All right, so the last thing we're going to do is talk about the parametric equation of a line. And this is going to be very brief, because all I want to do is define the equation of a line for you in 3 dimensions, and then I can give you some examples to work on your own and get you out of here. So, define parametric equations for a line L that contains point P sub O, and then it's parallel to given vector V. Use the fact that the displacement vector between the given point P sub O and arbitrary point P on the line must be parallel to that. That's like, okay, cool. You read words off of a piece of paper for us. That's wonderful. An explanation, if you please. You know, so what that's saying is that you have some line in space. And I'll put some arrows on it. That is not an arrow. That line, by definition, has to be parallel to some given vector. All right, so I'm going to create a vector that we're going to call ABC, vector V. That's parallel to that arbitrary line. All right, so that line, pretend it's parallel. Make it look parallel on your papers, because apparently I can't draw parallel. Milk, eggs, and strawberries. Good to know. All right, so what we're getting at is that a vector parallel to ABC would have to be some kind of scalar multiple of ABC itself. All right. So all I have to do is create a vector living along that line. That we'll call that line L. All right, because they told us to. I'm going to plot 2 arbitrary points on that line. One P sub O, the starting point, and the other P. All right, and that's going to create a vector as a subset of that line. All right, what I want is the displacement vector between P and P sub O, or starting at P sub O. So P sub O going to P is going to be the difference between the values that make up P and P sub O. So X minus X sub O Y minus Y sub O, cripes, and Z minus Z sub O. So if I multiply this vector V by some scalar, I should get P sub O P. All right? So that scalar that I'm choosing to multiply is a parameter. So I'm going to multiply it by a parameter that I choose to call T, because thinking back to the first unit, when we have parametric equations, we talked about time as being a parameter of some other kind of function. So if I have X and Y, yeah, that's great. That'll give me the path. But if I want to define movement along that path, it's usually in terms of time. All right, so let T equal the parameter. And this is going to be a scalar. So, and what ends up happening here is that if I take vector V and multiply it by T, that was actually red, multiply it by T, I'm going to get a result of the displacement vector P sub O times P, times P, P sub O P. Now I could actually carry out the process, because Z is ABC, so I could say TA, TB, TC is going to be equal to all this jazz up here, P sub OP. All right, now if there's going to be equality here, then T times A should be equal to X minus X sub O. That's where our first formula comes from. So I can make a little note here. And I won't take you through each of them, but I'll just show you this case. TA would be equal to X minus X sub O. If I add X sub O to both sides, that's going to give me, as a result, X equals X sub O plus TA. Which is actually my first rule. All right? You do the same thing for TB equals Y minus Y sub O. You'll get the second part of the rule. And then TC is equal to Z minus Z sub O. All right, which gives you the third part of the rule. All right. So the vector form of a linear equation actually ends up being the three components put together: X, Y, Z, X sub O plus TA, comma, Y sub O plus TB, comma, Z sub O plus TC. And we're actually not going to worry about the symmetric equations.
Plus C sub O? Or no, just the three together.
Yeah, just the three together, yeah. No, that's cool. Well, I guess you don't have to scribble it out. We're just not going to bother with it. I mean, those are the rules that give us the symmetric form. There's just not much we're going to do with it. So I guess I don't need to scribble it out. I'm just not gonna do anything with it. But if you want to scribble it out, by all means. You're generally scribbling stuff out. It just looks ugly enough. But you can write a little note, disregard, because all this is each one of these equations solved for t and then set equal to one another. I don't think you need to define it in any particular way in order to come up with those rules. So any question that asks you to come up with symmetric equations, we're not going to bother with. We only care about the parametric equations because what we end up here with are vectors that involve variables, not just scalars. All right? Sorry. So there are going to be variable vectors, which are known as vector valued functions. And these are the things that we're going to be able to do calculus to. And we're going to have to be able to kind of take our knowledge of vectors in their scalar form and apply it to function-related vectors and then go from there. So a lot of interesting stuff coming ahead. But what I would want you to try to do is see if you could figure out the solution to numbers 1 and 2 on your own before I go through the process for you, just using these ideas. Because if you could figure it out, I mean, I could give you the same spiel every single time. If you could figure it out before I end up spoiling it for you, then you're already ahead of the game. All right. So if you can't, that's fine. This is where we'll pick up next time. But at least give it a shot. A little tip, A, B, and C represent the parallel vectors. So the idea would be that if somewhere along the lines, you're going to have to figure out a vector that corresponds with these 2 points. So that's a good place to start. All right, and then if you don't get beyond that, that's fine. We'll pick up with it next time. But if you do, then you'll be ahead of the game, like I said. All right, so now it's good. Yeah, I don't know why that would happen, but that was a weird glitch. Okay, so these questions are asking us to find the parametric lines, well, parametric equations of the lines. Line passing through these points. So we're going to learn how to do that based off of the formulas that we discovered last class, and then we're going to learn how to find the intersection between those lines. It'll be pretty interesting stuff, I think. All right. So what we have to do is find parallel vectors. So one thing you could do just off the bat is designate one point as being your x sub o, y sub o, z sub o. It doesn't matter which one is which, but whatever one you designate as your start, that's what you're working off of from there on out. So, regardless of which one's more convenient, I tend to just let the first one I see be x sub o, y sub o, z sub o. All right, so that part of our parametric set of equations is going to be already accounted for. So now, in order to find the ABC, this is the parallel vector. What I'm going to do is find the displacement vector between these two coordinates, right? Any multiple of this displacement vector would necessarily have to be parallel. All right, so -3 minus 1, 5 minus 4, and 0 minus -2. So -4, 1, 2. Sure.
What do we label the second one? Do we just call it anything, like x sub 4, x sub 1?
Yeah, you don't even have to label it anything, but if you were,
The vector.
Oh,
On
yeah,
the
I
direction
did
vector.
that. I did PQ with the arrow.
oh yeah, that's fine.
That's fine?
Yeah,
Okay.
yeah, you can label it anything you want because ultimately we're just developing an equation that would pass through either of these points, so it's not going to matter which is which anyway. But in the next one they call it P and Q, so we'll use that notation. All right, so my equation in parametric form is going to be x sub o plus TA. So x sub o is 1 plus, here's my a value is -4. So plus t times -4, so minus 4t, comma, y sub o, which is 4, and my second entry is a +1. So plus TB, so plus 1B, 1T, sorry. So plus T. And then the last one is going to be -2 plus TC. The C value is 2. So plus 2C, plus 2T. I keep saying the wrong thing, which is generally not a good thing.
Is that how you want us to write it? I did like x equals 1 minus 4t.
If you write it as x equals y equals z equals, that's fine too.
Okay.
Yeah, both of them are equivalent, or both ways of writing it are equivalent. The way I'm writing it here is in the form of a vector valued function. It's a little bit more concise, but it's not any more or less correct. All right, so for number 2, find parametric equations of the line segments connect. Oh, before I even move on to that, notice how in this case we've moved beyond the calculator, the graphing calculator, to be able to verify that this is correct because we're in 3 dimensions. So, like if we were dealing with 2 space, we could do this work and then plug it into our calculator in parametric form, and everything will be fine. You could verify it out. But the best we can do here is check to see if for 0, we get the original coordinate, and for 1, we get the second coordinate. All right, because really what we're getting with the displacement vector is what would happen after t is equal to 1. So if I plug in a 0 for t, that's easy enough. You see it's going to be 1, 4, -2, because the t parts are going to cancel out. But if I plug in a 1 for t, I get 1 minus 4 is -3. 4 plus 1 is 5. And -2 plus 2 is going to give me a 0. So it checks out. So it's a little bit more manual, but definitely doable. All right. Now, when you get into things like magnitude, like this is a vector. So things like unit vectors, magnitudes, when we get to tangents or derivatives related to this stuff, we could talk about tangent vectors. These are all things that are going to come into play. Now that we have functions, I mean, where's the limit? Like it doesn't have to be just linear functions or constant functions anymore. It could be quadratic, any kind of polynomial function. It could be a set of trig functions, exponential functions, logarithmic functions. So basically everything's fair game. All right. One of the things that I'm fond of saying is that the hardest thing about any math class specifically that you're in is the class that came before it. That's not as true for this class as it is for most other classes. I would say the hardest thing about this class is the class that came 2 classes before it, right? Because if you don't know your derivative rules, then things start getting a little dicey. But if you really think about it, up until this point, everything that we've covered in this unit has been either brand new, so from the ground up, or if you happen to take a physics class, you've seen before, right? So, but it's not reliant. I mean, I think we'll all agree it's not reliant on anything that you did in Calc 1 or Calc 2, all right? But we're going to slowly start introducing the Calc 1, and then in the next unit, well, a little bit of Calc 2, but very basic, and then in the next unit, a lot more of the Calc 2 stuff. But it'll never get to the point where, like the things that made Calc 2 hard, those concepts will never really be a deterrent in this course, right? So a little bit of how to check it and a little bit of a motivational speech, I think. All right, so figure out ABC. All right, so that's your parallel vector, which again is the displacement vector between your 2 coordinates. So you could look at it as, like we were saying before, vector PQ. So 3 minus 2, -1 minus 1, 3 minus 4. You wouldn't have to show this step. If you actually just come up with the parallel vector, that's fine by me. It's just I find that when I skip this step in class, then people follow my lead and they skip the step, and then like half the class screws it up on the test. So I'm hoping to save everybody from themselves a little bit. All right. Choose one of the 2 points as, well, we've actually already made the choice. So this is x sub o, y sub o, z sub o. All right. Once I did p to q as my displacement vector, that forced my first value to be p. All right. If I did the displacement vector in reverse, if I did q to p, then my x sub o, y sub o, z sub o would have been q, but that didn't happen. So my equation I'll just write the x sub o, y sub o, z sub o parts. So 2, 1, little space, 4. So plus t minus 2t minus t. All right, all coming from these values here. Right, let me try something. I just realized what was going on with the highlighter. It's only when the writing is locked in, so I can't erase it, that the highlighter doesn't smear it out. It actually just starts highlighting it. But until the handwriting is non-editable, it still runs the risk of smearing it out. I guess for the artists, like the real ones. They want to blend colors and stuff. All right, but that's a parametric set of equations. Now we could graph those. We could see what this path looks like on GeoGebra. We could do it by hand, but I can tell you right now, that sucks. All right, we'll actually do a couple of graphs, but not for linear cases, because graphing a line in 3-space is like graphing a line in 2-space. It's like, oh, cool, we graphed a line. We want to save any instance in which we're creating graphs for the more interesting cases. All right, and so that's coming, but we're not quite there. So number 3, more equations, but we kind of have to do them because in order to determine the answer to number 5, we have to do numbers 3 and 4. So what I'm going to do is I'm just going to crank these out real quick, because number 3, they just flat out gave us the displacement vector. All right, they told us ABC, and they told us the point. So x sub O, y sub O, z sub O. So 3 minus t, 1 plus 6t, and 4 minus 3t. I can't hear myself think. All right, so the second one, find the equation of the line containing. So I need to figure out my ABC, the parallel vector. So parallel vector, again, displacement vector. So 4, -3, 5. All right, so this makes this my x sub O, y sub O, z sub O. So I'm looking at 1 plus 4t, 1 minus 3t, and 2 plus 5t. All right, so those are my my parametric equations representing the lines passing through those points. Great. Now I want to figure out if they're going to intersect one another. All right. So this is where things get a little interesting, because there's a couple of different ways that this could play out. But I'm going to kind of lead you to the most appropriate way to do it. Okay, because they're asking for the intersection of 2 lines. All right. Now, units are kind of an important thing here. I mean, they're more than kind of. They're definitely an important thing. Right? The fact that the units were not defined tells us that we don't know that these are kind of operating on the same time frame. So the first problem could be working in hours, and the second problem could be working in minutes. And maybe T doesn't even represent time at all. Maybe it represents temperature. One's in Fahrenheit and the other's in Celsius. Right? The idea is that not all T's are going to be created equally. So I have to be able to distinguish from one T to the other, because if I were to assume, and I'll just kind of play this out logically, if I were to assume that this T were the same as that T, then what would be, the assumption would be that not only are the paths crossing each other, but they're crossing each other at the same time, right? So I look at two possible ways of thinking about this. Both of them involve the intersection of two roads, all right? So back to the cars, always cars. So you could have two roads crossing, no problem with that, right? We see that all the time.
Yeah.
Two cars crossing. Every now and then you see that, right? Yeah, it's terrible to see. I've actually only seen a collision, like a live collision once, like, and it wasn't even like from beginning to end. It was more like out of the corner of my eye, I saw something going down, and then as I was turning my head into my field of vision, I could see like the last moment of it happening. But that was really it. So like at this point in time, it's like once in a lifetime for me anyway. So it's completely anecdotal, but bottom line is you don't need the two cars to collide in order for the roads to intersect. All right? If T here needed to be the same as T there, that would mean, and forget about cars because that's kind of morbid, as they're paving the roads, like as they're creating the roadways, they would have had to be creating the intersection in such a way that both roads are crossing each other at the same time as the pavement is being laid down. All right? That's not necessarily the case. One road could have been paved first, and then later on the other road could have been put in. All right, bottom line is after the fact, the two roads are there and they cross. All right? Yeah, but it was crazy. I was on the Garden State Parkway, and I was on my way to my wedding rehearsal, and I was in the driver's seat, and I heard my friend in the back seat. He was like, "Whoa, whoa, whoa!" And it just like it was just a weird thing to be yelling out. I was like, "What the hell?" So I turned around and I looked, and as I'm looking, I can see the car as it's slamming into the sidewall of the highway. It's like he described it like they were trying to do a lane change. You know, like you're gonna merge left. You don't realize someone's in your blind spot. So people do that all the time. They swerve back. This person overcompensated and then went right off the road into the guardrail. It's like, oh my God. But I saw it was like, boom. That was pretty insane.
So I hate it when people in the right lane, they don't realize somebody's about to merge. Go on your left side. So I always notice, I kind of like trying to figure out like, hey, I'm gonna probably be at the same. He's gonna probably exit at the same time where I'm on the right side. Let me merge into the left side, give him some room.
Yeah. Yeah, it's just common sense at that
right?
point. Yeah.
I hate that too, cause like.
It's not a race. Like I'll let you on. You know, like just I'll do that. Just do that when I'm trying to get on. You know, but people don't think. So accidents happen. But here we're just looking to see will the roads intersect. So what I'm going to do is I am going to put a little subscript here. I'm going to call this T sub 1 as soon as my pen turns back on. T sub 1. And this will be T sub 2. I mean, as long as you distinguish one from the other, you're fine. So maybe you just leave one as T and the other you call T sub 2 or T sub 1. All right, one way or the other, it's okay. So if this is going to play out correctly, what I need is for 3 minus T1.
Could you give her a different letter if you want?
You could, yeah. In this context, absolutely. There are some other problems down the line where we're going to use other letters for other things. So I try to stay away from it. Like I've seen some textbooks, and even I've done this in the past. They've called it like T and S. And I was like, all right, that's fine. S means something else. But the problem in my mind is that, well, there's a lot of problems in my mind. S stands for something else that we're going to cover down the line. I mean, well, we've already covered it. It's arc length. But we're going to learn how to parameterize equations in terms of the arc length of a function. whatever that means. That'll be a fascinating conversation. It's a little mind-bending, a little trippy, but it'll be fun. So if there's going to be an intersection, the first equation has to have some t value that'll get it to a location that corresponds with the location that the other equation gets to based on its own t value. All right, so they both have to get to the same location, but based on their own set of rules. All right, parallel dimensions. There's a portal. All right, so you got Earth 1 and Earth 2. Earth 1's portal is in New York, Earth 2's portal is in London. But they're at the same location in space-time. So if I go through that one portal in New York on Earth 1, it'll bring me out in London on Earth 2, two different locations based on their own sets of rules based on geography and physics. But bottom line is it's the same physical universal location, all right, or multiversal. Although, I don't know if you're all caught up, but Earth 2, no bueno. I don't know how many Arrowverse fans there are, but you have not. All right, so I will not.
I know the gist of it, the multiple
Yeah.
universes that have come together so far.
Yeah, it's happening. It's happening. There's some big goings on. Happened last night in Arrow.
I don't think I've watched since Rachel Gould.
Oh, so season 2 of Arrow, I think. Yeah, season 3.
Yeah.
Season 3, because season 1 was The Undertaking, season 2 was Deathstroke, season 3 was Rage. So, yeah, but you know what? You could pick up with Arrow, you could pick up right now and be good, because this is the final season, there's only 8 episodes, and it's going to set you right up nicely for the crossover, Crisis on Infinite Earths, which comes out at the end of November. 6-part crossover? Maybe. Supergirl, Batwoman, Flash, and Arrow. Legends might have one in the back end, but there's going to be a cliffhanger, and then they'll pick it up in the new year.
Arrow was really good for like season 1 and 2. After that, season 3 was alright, and
Then it started taking a dive.
yeah, a really big dive. But the first 2 seasons were strong.
Oh yeah,
They
Absolutely.
Really got me, but I didn't like it afterwards.
but you know what? Like the episode last night, they brought you right back to episode 1
Oh really?
and replayed episode 1, but with a slightly different viewpoint. Like it was pretty solid. So definitely worth the watch, I think. But so my Arrowverse analogies aren't going to always land, but sometimes they will. What we have here is a system of equations with 2 variables, 3 equations, 2 variables. So we're probably going to get some kind of solution. It's just a question of, will we get a unique solution, or will we get infinitely many solutions? Or will we get some kind of contradiction, I guess. But generally, if you have 2 equations, 2 variables, you're looking at some kind of solution coming out of it. Here we got 3 equations, so even better. All right. So you do it algebraically, or we could use the calculator to do the work for us, all right, in the form of a matrix. So what I'm going to do is I'm going to get it so that it's in standard form. So variables on the left and constants on the right. All right, so I'm going to bring the negative 4t2 over to the left. So I'll have negative t1 minus 4t2 equals negative 2, because I'm just going to subtract the 3. And then 6t1 plus 3t2. That looks like a clean 0 unless I screwed something up. Always possible. All right. And then -2. This is one of those situations where if you had to do it out algebraically, you're not going to spend too much time. You should be fine because the second equation is nice and convenient. You could solve for T2 pretty easily in terms of T1 or vice versa. But we'll use the calculator. We talked about this in the last unit when we went over some of those word problems with vectors. So it's the same general idea. We're going to make a matrix out of this and use that magical RF technique. All right, so we have to put it in the calculator. So 3 by 3, so we're still good there. You'll get to a point when you'll be so spoiled with the calculator that even things like this will be like, oh man, I gotta put another matrix in. This is annoying. It's taking forever. Because you will have completely lost sight of the fact that this is kind of a pain to do by hand algebraically. And the reason you will have lost sight of it is because I will have never asked you to do it by hand algebraically. So you'll be like, you start forgetting what the amount of work is entailed with the kind of problems that, like you don't have to worry about, right? So you kind of create a new normal where this is even too much for you. You're like, oh man, I gotta type another matrix in. But, just in those moments, I don't know, I guess try to imagine a world where you have to do this, which is basically every other Calc 3 linear algebra teacher. So, anyway, doing a quick double check to make sure my data's in correctly. I think I'm all right. Gonna quit it. So then, RF, then select matrix A, and we get that. Oh, look at that. Must have done something wrong. Not really. Not the case at all. I'm gonna convert this over to fraction form by hitting math and then option 1. So that's a nicer version of it. Is there a way to get it all on the same screen? No, I don't think so. Well, I guess I could try it this way. No, that's just not going to happen. Although, I could go old school. No, I can't expand it. I was hoping. Bring this back. All right, well, I'll just take the fractional one and paste that in. Well, I don't even have to paste it in because it's actually fairly convenient. So 1, 0, -2 sevenths, 0, 1, 4 sevenths, 0, 0, 0. All right. Now, each column would represent a variable. All right. So if I read this across the top, what I'd be looking at is 1t1 plus 0t2 is equal to -2 sevenths. And then 0t1 plus 1t2 would be equal to 4 sevenths. And then the last row, I'll write it, but you'll see very quickly that it's not very meaningful in this context. 0 T1 plus 0 T2 is equal to 0. All right, so if you clean that up a little bit, you get the relevant pieces, which tells me that T1 is equal to negative 2/7. T2 is equal to 4/7. And then the last thing is saying that 0 is equal to 0. All right, cool. 0 is equal to 0. I didn't need that piece of information, but it was given to me because, again, ideally I'd have 2 equations, 2 variables. I had 3 equations, 2 variables. I had 1 extraneous equation, 1 equation that was unnecessary. I could have got the job done with 2 out of the 3 equations. I didn't know which pair I wanted to pick, so I just used them all in the RRF, and the calculator made the choice for me. So that's great news. Now, because we got solutions for T1 and T2, we know that there's going to be an intersection. Now, that's all they asked us to do here. But a question could ask you to determine where they intersect, so we might as well figure that out. So I'll take my, well, it's visible on my screen right now, so I'll take my second equation. So 1 plus 4T2, comma 1 minus 3T2, comma 2 plus 5T2, where T2 is equal to 4/7. All right, and that'll give me the solution vector, which in theory would be the same as whatever I would get if I plugged in T1 for my first equation, which you could use as a good way of checking your work, but not a requirement. If we're just looking for the intersection, what's good for one will be good for the other. So 1 plus 4 times 4/7, ugly decimal, so math bracket, 23/7. One minus 3 times 4/7. And this is just because I want to take a break from thinking. Negative 5/7. And then 2 plus 5 times 4/7. Math bracket, 34/7. All right, so intersection exists. All right, and again, if you wanted to, you could have plugged your T1 value, the negative 2/7, plug that into your T1 set of equations, and you would have gotten the same coordinates, 23/7, negative 5/7, and 34/7. All right, so that's giving us the location of the intersection between the 2 roads. Now, it's also telling me that time isn't flowing the same way in these 2 systems, assuming T represents time, right? Because it takes negative 2/7 in order for T1 to hit that intersection, and 4/7 for T2 to hit that intersection, right? So if you're designating 0 as the start of the clock, then, like you're standing there with a stopwatch, and you're just, cars are just driving by. You start the clock, negative 2/7 of a second prior to you starting the clock, this first car was already through the intersection, all right? 4/7 of a second after that, the second car was through the intersection, all right? So, a physical application of this would be, well, is there a collision? I don't know that I'm qualified to answer that because I don't know how fast, you know, like what kind of intersection are we talking about here? Like if somebody blew a red light going 30 miles an hour at a busy intersection, that kind of thing, like would they be through it in like half a second, or would it take longer than that? I don't know. But it would beg the question of, you know, like what are some of the implications of this kind of information? So in order for there to be actually physically a collision, do these two numbers have to be precisely the same? No. If they're very, very close to one another, then that could be good enough to indicate that there is a collision. All right. It may not be a. It
Even
could.
though the times are not the same,
Yeah.
you consider that to be because they're right close.
Yeah, because maybe one car is taking off the tail bumper of the other car.
So it's like.
One's a smart car, one's a fire engine.
Exactly. Those smart cars, man.
What
Smart car
degree
driven
can,
by a fire truck, I don't think could be a smart car.
Yeah, nobody's thinking that's a smart car when that happens. Yeah, I feel like those cars are just designed for like, do you sign a waiver when you buy it? Like, listen, you get in a crash, you're dead. Like, that's it.
No, that's correct. Like,
Yeah.
you'll die.
Yeah, you don't like, that's it.
There's no cushion.
Yeah, there's nothing. With crumple zone, you are the crumple zone.
Anything bigger than a squirrel, you're done.
Yeah. I mean, a squirrel will be enough to do it. Like, most cars, you hit a deer, you're like, ah, there goes my hood. You hit a squirrel in a smart car, and that's the end of it. Yeah.
keep the deer doesn't
Totaled.
do you, especially on the hutch. Oh my God, there's no way out.
Yeah, exactly. I mean, what shoulder? What shoulder? There's none. Okay, so distance between a point and a line. All right, so we just found the intersection between a point and a line, so now we have the distance between the point and the line. So definition of this is really, I mean, it's fairly straightforward. It's the cross product between, we're calling it PM. And if we look at the diagram, PM is the distance that we're actually looking for, and vector V, all right, over the magnitude of V. So I'll get into the derivation, I think, next time, because it's going to kind of bring things to a screeching halt at this point. But in terms of the actual process, it's not terrible. We just need to come up with the relevant vectors. When it says find the distance between the point 0, 3, 6 and the line with parametric equations 1 minus t, 1 plus 2t, and then 5 plus 3t, we're looking at 1, negative 1, I was looking at the wrong thing, 2, 3 as my parallel vector. X sub O, Y sub O, Z sub O. I'm just kind of working backwards from the parametric form. The coordinate, which we're calling point P, is going to be equal to, that's the 115. Now my pen doesn't want to cooperate. All right, so that's all information I'm pulling from the parametric equations. Okay. This point here is 0, 3, 6. That's the point M based off of this diagram. That's the point in space. All right, so I need the displacement vector P to M, which once you have everything labeled up isn't bad. So we're pinning it at P. We're looking at negative 1, oh, I'll write it out, 0 minus 1, 3 minus 1, 6 minus 5, which gives me negative 1, 2, 1. All right, so that's my P to M. We need to cross that with V and then use that and divide that by its the vector magnitude. All right, so the magnitude of the cross product, there's a shortcut formula for that, but we talked about it last time. It's kind of like 6 of one, half a dozen the other, because like in terms of the preference, it could be fine. I would determine whether or not it's valid, or not valid, valid's not the right word, a good idea to use the shortcut rule. I would make that determination based on whether or not I was given an angle. Because we were talking about it last time, it's kind of more trouble than it's worth to use the shortcut rule, which ends up not being much of a shortcut if you have to solve for the angle to begin with. All right, if you have to use that cosine rule, u dot v over the magnitudes multiplied, to figure out what theta is, to then plug it into your magnitude of u times v times the sine of theta, it's like, I feel like I'm doing way too much work for something like that. So in this context, I think it ends up being easier to just find the cross product of PM and vector V, and then find the magnitude after the fact. All right, so IJK, PM is -1, 2, 1. V is -1, 2, 3. It's up to you if you want to get the framework out the way I'm doing it here. I find that people who struggle with the concept of the cross product, they don't struggle with the mechanics of it. They just forget that the J term is supposed to be negative. And so a little reminder to yourself might not be the worst idea in the world. Right, so for the I, I'm going to just, I know I'm not really covering anything up here, but pretend I am. Diagonal down minus diagonal up for the JK. So 6 minus 2 is going to be a 4. Then for the J, so diagonal down is going to be -3. Diagonal up is going to be -1. But we're looking at diagonal down minus up, diagonal up. So -3 minus a -1, so -2. All right. So -2 is going to be the result, but we already have a negative built in, so +2. Actually, I'm going to leave that showing a little purple there to show that I changed it from negative to positive. And then K, diagonal down -2, diagonal up -2, -2 minus -2, so -2 plus 2, so that zeroes out. All right. So the magnitude of PM by V is going to be the squared values added together. You don't have to write 0 squared if you don't want, but just for note-taking purposes, I'll throw it in there. Rad 20. We also need the magnitude of vector V. All right, so that's this guy here, vector V. So magnitude of V, -1 squared plus 2 squared plus 3 squared. I'll put it below. So the square root, we got 1 plus 4 plus 9. So it looks like the square root of 14. All right, and so the distance between these 2 points is just going to be the quotient. All right, so the distance is going to be the square root of 20 over the square root of 14. And you can simplify if you want. I mean, there's not much to simplify in this case. Divide top and bottom by 2, so 10/7. But in terms of a decimal value, I don't think there's any more benefit to having a decimal than there is having a fractional value. All right, but that's, I'm kind of debating now. Maybe I will get into the yeah, I'll just give you the short version. It's not really too much of a proof as much as it is a demonstration. So if I go to my diagram there, and oh, I just realized I cut off some of this stuff. If I go to my diagram and create a rectangle out of the relevant pieces, so if I were to find the magnitude of the cross product, that's equal to the area of that. In this diagram, it actually ends up being a rectangle, but it's the area of the parallelogram. All right, so PM crossed with V, so the magnitude of V, so here's V itself, this piece. Because all of our vectors are displacement vectors, they're going to be pinned at the origin. All right, so area of a parallelogram is base times height. All right, so I'm saying that PM crossed with V would be equal to the base times the height. Now the base here can be thought of as the magnitude of vector V. The height can be thought of as the magnitude of, well, we're calling it D, but it's really the magnitude of PM. All right, so I'll just write magnitude of PM. All right, so really it's just going to be magnitude of V multiplied by the magnitude of PM. But the magnitude of PM itself is the distance that we're looking for. So distance multiplied by the magnitude of V would be equal to the cross product's magnitude. And so if I just divide both sides by the magnitude of V, the scalar value, the magnitude of V, I get the resulting value for distance. Stay away from purple there, I guess. And so that's where the formula comes from. And it's kind of a cool origin story, but it's kind of interesting to think that when we start talking about multivariables situations, that there's actually going to be an even cooler way to figure out the distance between a point in a line in space, a point in any curve. And it's going to involve partial derivatives, so exciting times ahead. All right, but we're still in the foundational part of things because we just learned how to define a line in 3 dimensions. So, fun fact, by learning how to define a line in 3 dimensions, we've actually learned how to define a line in 4 dimensions, 5 dimensions, 20 dimensions, it doesn't matter. Because we just basically discovered on the previous page anyway, that we're gonna define them parametrically. So parametrically is just telling us that however many dimensions you are, you need to have a component within your vector value function, to represent each one of those dimensions. All right, so if I'm working in 4-dimensional space, I have to have a component for x. Well, once I get out of x, y, z, if I go into 4 dimensions, instead of saying x, y, z, I'll say x sub 1, y sub 1, z sub 1. I keep doing that. X sub 1, x sub 2, x sub 3. When I get into 4-dimensional space, I'll just add an x sub 4, 5th dimensional x sub 5. It makes it a little easier because if I go to 20th dimensions, then it would be x of 20, and then I could use some knowledges from sequences and series from Calc 2 to be able to streamline the process a little bit. But if I have, let's say, 6 dimensions, all that's telling me is that I have to have 6 components to my vector, all right? But it's still gonna have the same structure. I would still need to have a parallel vector. I would still need to have a starting point, all right? So you're like, well, what would a vector look like in 6-dimensional space? Well, it's not really so much of a question of what the vector would look like. It's more so, what would the coordinate axes look like? You know, because at some point you start running out of ways to represent different dimensions. You'd have length, width, height, but then maybe you would define the width as being kind of an angular rotation away from the x-axis and call that the y-axis, and then another movement, the z-axis, and so on. Right? So we'll explore all that stuff down the line and how you could actually geometrically make sense of higher order dimensions. Right? But for now, basically, since we've covered everything that there is to cover about lines, let's talk about the next dimensional representation of a geometric figure in coordinate geometry, and that would be a plane. Right? So what a line is to 2 dimensions is what a plane would be to 3 dimensions. So lines can be parallel in 2 dimensions, or they can intersect. Those are your only 2 possibilities. If they're not parallel, they must intersect. Right? In 3 dimensions, lines can be parallel, they can intersect, or maybe they could be neither. Right? These 2 lines are neither parallel, nor do they intersect. They're skew lines. All right? But planes in 3 dimensions, possibilities, they're either going to be parallel. This is even parallel. Right? Parallel. If they're a restricted domain, maybe it's like a strip of a rectangle in one direction, a strip of a rectangle in another direction, but they are parallel because they're equidistant from one another in the relevant locations. Or they're going to intersect. All right? So if the 2 planes are not perfectly parallel to one another, at some point they're going to intersect. All right? So what happens for lines in 2 dimensions is what's going to happen for planes in 3 dimensions. There's no way for them to be askew, right? But if you take 2 planes and put them in the 4th dimension, now you could have planes that are either parallel, intersecting, or completely missing one another, all right? Because we're introducing an additional dimension, all right? More on that later. But for now, all we're going to do is explore how on earth, how do you write the equation of a plane, and then how do you graph it, right? So what we look for here is something called a normal vector. All right, a normal vector is a vector that we know is orthogonal to the plane. All right, so it has to form a 90-degree angle with the plane. And the conclusions you draw about your normal vector will also dictate the same conclusions for the planes themselves. All right. So now orthogonality is based on the dot product. So if 2 elements, 2 things are orthogonal to one another, their dot product is equal to 0. So I'm defining a vector that's living in the plane as PQ. So this is a vector that's on the plane. And the other vector, the one that's defining the nature of the plane, is the one that has to be normal to it. Normal vector. All right. They have to come together to form a right angle. So they have to be orthogonal to one another. So the normal vector we define as ABC. I'm going to go red for that one. PQ is the displacement vector between x sub o, y sub o, z sub o, and x, y, z. So that's going to just be x minus x sub o y minus y sub o, z minus z sub o. That result needs to be equal to 0. That is the definition of a plane. All right, but I don't want to write it like that. That's ugly. Let's clean it up. Let's find the actual dot product between these two vectors. So I'm going to run the A through, and I'm going to run the B through. So just distribute it through its corresponding parts. And I'm going to need a fresh color here. Oh, I'll just use, well, I already used black. I'll just jazz it up here. There's nothing to do but get a little spicy. Custom color palette. I need like a nice green. Let's see, is that visible? Yeah, reasonably visible. All right, so we're looking at AX minus AX sub O plus BY minus BY sub O plus CZ minus CZ sub O equals 0. Fell down. I'm going to clean things up because AX sub O, BY sub O, and CZ sub O, those are all going to be scalar values. The variable stuff I want to keep on the left, so we're going to have AX plus BY plus CZ, and then everything else is going to go to the right. So AX sub O plus BY sub O plus CZ sub O. So what we've ended up kind of deciding upon, and I say we as if I had any say in this, decided to let the whole right-hand side equal some constant d. Just some made-up value. Not really. Where d is equal to the dot product between n and p. Or vector p. Kind of streamlines it a little bit, makes it a little bit cleaner. It's kind of like conic sections. Like when you're graphing an ellipse or something like that, it's x squared over a squared and y squared over b squared. It's like, well, a and b mean something. As long as you know what they mean, you know how to graph the ellipse.
Wait, what does D mean here?
D is going to be the dot product between the normal vector and the vector going to P. So we're just dotting these two values. Okay? And that's really what this is the result of. So if I undot this, this is what the expression that would be, that represents that. Not so good with the grammar, but hopefully I got that idea across.
Is P the same as P here?
No, just the P. Because P is x sub o, y sub o, z sub o. So if I were to create a vector to point P from 0, it would be vector P is x sub o, y sub o, z sub o, just with the triangular brackets on it.
It's not the unit vector. P is not the unit vector.
No.
It's just the base vector.
Just some displacement vector from 0.
Vector from
Yeah.
It's what they call the base vector, like something like the base that's going.
Yeah, that's another name for it, yeah. All right, so in number 6, it's asking us to find the equation of a plane connecting or containing the points and perpendicular to the given vector. So it's actually very straightforward. So all we're gonna do is just kind of label this up a little bit. So if it's gonna be perpendicular to the vector of 3, 3, 6, then that's making n 3, 3, 6. If it's going through this point, 2, 2, 1, that's going to be my point P, 2, 2, 1. So I just need vector P, which is going to be also 2, 2, 1. Then I need D, which is the dot product of N and P. Which is 18. So that gives you the right-hand side of your equation, which is really the only challenging part of it, because the normal vector is made up of your A, B, and C values. Which serve as the coefficients of x, y, z on the left-hand side. So I'm looking at 3x plus 3y plus 6z is equal to 18. That's the equation of the plane. Now I just want to graph that. Now the reality is, if I'm graphing a plane, the correct way to do it would be to take your piece of paper, lay it flat on the desk, take the side, like when you're shading using a pencil, take that side of the pencil, start in the upper left-hand corner of the paper, and start shading. And then after about 20 minutes or so, you will have shaded the entire piece of paper. All right, shaded from upper left all the way to the lower right, hitting every square inch of the surface of the piece of paper, because planes are infinite. All right, length, width. If you were to properly graph a plane, it would cover your entire sheet of paper. All right, so that's not a good way to do it. We don't want to do it that way. What we're going to do is graph a triangular cross section of the plane consistent with the x, y, and z intercepts. All right, so that's all we're going to do. We're going to find the x, y, z intercepts, and then we're going to connect them, and then we're going to shade that portion of it in, which is actually not hard at all. So x-intercept, you get that by letting y and z equal 0. 3x plus 3 times 0 plus 6 times 0 is equal to 18. You wouldn't have to show that work. You could just write 3x is equal to 18, getting x equal to 6. For the y-intercept, you let x and z equal 0. Leave y variable. The same idea as what you would do if you were graphing x and y intercepts in the two-dimensional system. You just let the other variable equal 0. Here you just have a couple of other variables. All right, so the z-intercept, let x and y equal 0. and you get your z-intercept. So you just have to plot those. Now the things that make plotting on a coordinate, on a three-dimensional system challenging won't really play a role here because we're living on the axes. All right, so 6 steps, 2, 3, 4, 5, 6 in the direction of x, 6 steps in the direction of y, and 3 steps in the direction of z. Connect them. I'll use my line draw tool because, you know. Oh, that sucked. Not any better. That one I'm going to have to freehand. Okay, pretty bad, but whatever. And then just shade that bad boy in. And this is a triangular cross section of your plane. Really all we needed to do is give us a sense of the orientation of the plane as it relates to the x, y, and z axis. Alright, so really not bad when you think of it that way. Alright, the big challenge is actually coming up with the equation of the plane to begin with. But that's not too terrible. It's actually fairly quick. It's that concept that I've been alluding to, I've been teasing for a while. It's called the vector value function. I've actually been working with it fairly frequently. It's just we haven't always had to call it a vector value function. In fact, this time in this particular semester, I've kind of made it more of a point to use that term earlier in the course just to kind of familiarize everybody with that vocabulary. Vector valued function is really just saying that you have a function that is incorporated into a vector in some capacity. So what does that mean? Well, anytime you have a function, you have everything that goes along with it, right? So you spend about 3 years maybe. I mean, if you're thinking in terms of college level type math, whether you did it in high school or college, or you kind of spread it out. But essentially like 6 courses, maybe 5 courses, 4 courses, depending if you skipped, but minimum 4 courses related to function mathematics. All right, so you're talking like your algebra, basic algebra, algebra 2, pre-calc, calc 1, calc 2, maybe you did some other courses in there, you know, like if you took differential equations or something like that. Right? These are all things that come into play. Maybe you took a science class that dealt with some functions also. Right? If you took a science class, you dealt with functions. You know, like anything that involved computation, because input-output is all function. All right? Getting an output for a given set of inputs, that is the definition of a function. All right? So everything that goes along with functions is going to come into play here, except we're going to look at it from, you know, through a vector lens. All right? So if you look at it here, you have an input. We're calling it a real number t. But the output is going to be f of t, g of t, h of t. All right? Okay, so maybe you don't like that. How about x of t, y of t, z of t? All right? It doesn't matter what you call it, it's all the same. You can use IJK notation, but bottom line is you're dealing with a vector that's made up of variable components. That could be as easy or as difficult as the vectors, or as the function itself. All right? So as the components that make up that vector. Right? If you're dealing with something that's got some crazy functions embedded into it, then it could be a little funky. But odds are it's not going to be something outside of your area of expertise. All right. So basically all this whole page is saying is that I can take any function, whether it's a parabola, a line, any kind of line, and represent it as a vector value function. All right? I could represent it as a vector containing variable quantities, all right? Which makes it very flexible, right? Because if I'm telling you that we can take vectors and expand it into 3 dimensions, 4 dimensions, 10 dimensions, what that's telling us is that I can take any function and expand it into 3 dimensions, 4 dimensions, 10 dimensions. I can take a parabola and put it into 5 space, all right? So as a parabola, not as a surface, all right? Just based on the concept of a vector value function. So pretty interesting segue into the next phase course, all right? But really all we're gonna talk about tonight is how to graph these things. Basic, all right? For number 1, this is almost precisely what we did in the first unit, except it looks like it's not even remotely like what we did in the first unit. This is like the first lesson of the first unit. When I gave you x equals this, y equals that, let's put it in our calculator, get a table of values. It's the same thing, all right? So there's no reason to be intimidated. You've seen this before, all right? This is saying that x is equal to 4t minus 1, all right? And y is equal to 2t plus 5. This is a set of parametric equations. In 2 space. I'll write it this way. Real space dimension 2, but it just means 2D. So how would you graph that? It's really not difficult. All you're going to do is make a table of values, an exhaustive table of values, complete with many, many numerical computations, hours of work. Not at all. Yeah, it's going to be a line. What do you need to draw a line? 2 points and a ruler. That's it, in 2 dimensions anyway. So I just need a couple of values. But the form that it's going to take is a little bit different, so I'm just going to kind of walk you through that really quickly. All right. So the question would be, well, what values of t make sense? My answer to that is, well, I guess look at the graph. I see an origin. All right, so I'm guessing that the x and y values are going to have to hit 0 at some point. All right, so I would take a look at my t value and see if there's some extreme values of t that would have to come into play here in order to make this value equal to 0. Well, in order to be 0, t has to be a quarter. All right, so I don't think t needs to be very extreme. So I can keep t pretty low. I can keep it around 0, maybe like -3, -2. Maybe I'll just do -2. Then I'll do a 0, and I'll do a +2. Really, I only need 2 points. Whenever I graph a line, I always just throw the third point in there in case I screwed up a calculation on one of the first 2. All right, because if it's going to be a line, the third one will be the tiebreaker. All right, if I get something that doesn't end up being collinear, then I know I screwed something up. All right, so if I plug in the t of -2 here, I'm going to get -8 minus 1 is -9. Plug in a -2 for the other one. -4 plus 5 is a +1. All right, that's the definition of stealing my own thunder. So I'm looking at a vector -9, 1. All right, so this is going to be a vector, and this is the part that's kind of a little bit different from the way you would draw a line. All right, that's definitely a little bit different. I'm gonna have to freehand that. I'm gonna have to zoom in and freehand it. All right, imagine that is a straight line vector. It's glorious. Yeah, it looks terrible. All right, so for the next value, 0 is going to be easy enough, -1, 5. That was super easy, barely an inconvenience. All right, so that's going to be my second vector. Now my third vector, I'm going to plug in a 2. This purple looks out of place now. I'm going to plug in a 2, so 8 minus 1 is 7. And 4 plus 5 is 9, so 7, 9. So 1, 2, 3, 4, 5, 6, 7. And then I think this is 9 up here because I think it's a 10 by 10. All right, so sketch the graph and find the Cartesian equation that describes the curve it traces out. All right, so these vectors are pointing to the coordinates that are on the line itself, but the vectors themselves are not part of the line. All right, so what I have to do now is connect those points. Come on, you son of a gun. Connect those points. That would be my line. The vectors, and this is the vector valued part of it, those vectors kind of serve as braces that hold that line up. All right, so you kind of look at them as supports to hold that line in place. Right? The more vectors I get in there, the more sure I'm going to be about the overall structure of this thing. But those vectors are pinning that line into its position. Now, because this is in 2 dimensions, I don't think we really needed that concept in order to really convey the idea. But you could see how, looking at it in 3 space, it would take on different meaning. I also need to come up with the equation of a line that exists here. So I could do that one of 2 ways. One way would be by points, and the other way would be to go back and do some substitutions. I don't like the idea of substituting like in Unit 1. What I would prefer to do is just find the slope between these corresponding points. So a little change in y or change in x. So we're talking 4 over 8, so 1/2. And then just choose a coordinate, doesn't matter which one. I'll take this one and put it into my point slope form of a linear function. Y equals m times x minus x sub 1 plus y sub 1. So we'd be looking at y equals 1/2 x minus 7 plus 9. All right, so we're able to snag this out, not based off of too much of what we did in the first unit, which would be solving for x in the first equation to plug it in for y in the second equation. It wouldn't be like that really at all. It's more so I'm going by points at the at this juncture. All right. So I'm going to put a star on numbers 2 and 3. So I exercised my teacherly right to do the really easy one in class to give you a sense of how it all works, and then leave the terrifyingly complicated one for you to do on your own. I will tell you that your best bet for attempting this kind of question would be to stick to unit circle numbers. Makes life a whole lot easier, all right? So, and what I mean by unit circle numbers is as you go around the unit circle, look for the values of theta that are convenient for both sine and cosine, which really just ends up being the ones on the axes, all right? So don't get into your pi over 4s, you know, you can have decimals everywhere. Just go in quarter terms, so 0, pi over 2 pi, 3 pi over 2, 2 pi, all right? Now, it's going to be an infinite relationship, but you may have to do a cycle or two before you can see what's going on. I just mistakenly gestured what the shape is supposed to look like. I kind of want you to discover that on your own. So I'm going to stop talking. All right. So it's supposed to be like a pleasant surprise. Oh, look what I just made. You know. So that's where I'm going to leave.